this system of Floc filter and plate settlers and Floc hopper and how that combo works. And you all know that I'm looking for a wonderful name to describe that system of three things: Floc filter, plate settlers, Floc hopper. I don't know how to talk about it. And because we do this in a different way than anyone else does it, I would like a name for this system so that I don't have to stumble over those three things every time I try to talk about it. So anyway, if you have any ideas, I would love to hear them. What I want to do today is just a very quick review in the next few minutes about what's going on inside that. And then we're going to look at a bunch of movies showing more about what's happening inside this system. So the review is looking at this image. Remember, there's red particles or small flocks that are the ones that never got very flocculated inside the flocculator. And their characteristic is that they're settling too slowly to be caught by the plate settlers. And so if we don't have a Floc filter, they just go right on out the top of this tank and go on to the filter. So red guys are the guys that we would like to reduce their concentration as much as possible. And remember, at the beginning of the process, like if you were looking upstream from the flocculator, right, where the water's coming in, all the particles are red guys at that point. All of them are particles that would have just gone right through the sedimentation tank. So if this isn't clear, if you turn off the chemical feed, the coagulant at the beginning of the plant, then you don't make any flocks. You only have red guys, and those red guys go washing right through the flocculator, right through the plate settler Floc filter system. Okay, that was red. The green guys, the green ones are flocks that grew inside the flocculator and grew large enough to be caught on the plate settlers. The blue ones are the ones that are made up of green ones that aggregated by rolling down, cascading, having an avalanche down a plate settler, and they combined, green ones combined into a blue one. And then the blue ones are able to settle fast enough that they actually hang out in the Floc filter. As the water is going up, they're settling by gravity and just hanging out. And the blue guys have a little bit of flow that goes right through them. And that's how they act like a filter. Some of the water that's going up through the Floc blanket goes right through those blue guys. And inside the blue Floc, there are lots of clay particles and other things that are kind of held in place by the coagulant. And as a clay particle goes up through there, there's a chance that it can collide with one of those particles and stick and remain inside that blue Floc and become eventually a blue Floc with lots of red particles inside it. And as it does that, it becomes more dense, its fractal dimension increases, its porosity decreases, and so very little flow of water goes through it anymore, and hence it's not able to capture any more red particles, and so it ends up being useless. Wow, that was a lot. Does anybody want to ask a question about that? Like why, or why does this matter? Or would you explain again how green dots form? Anybody want to ask a question? Okay, it's Tuesday and you're good. So we're going to go to, I'm going to keep on going. We're going to go to this system where we actually we make a tiny little tank representing this inside the lab. And we're going to look at what happens inside that system. And we did this because there were things that we ran into in the field, in the water treatment plants in the field, where it didn't work the way we expected it to. And the thing that actually wasn't working right is we weren't succeeding in getting Floc filters in the plants in Honduras, even though in the lab, we could make a Floc filter in an hour. And we couldn't figure out what were we doing wrong with the geometry that in the field it worked and in the lab, that in the lab it worked and in the field it didn't. So we built this system, and we're going to jump ahead to look at what happens when it's working, and then we'll come back to what was the geometry that was messing us up and was making it not work initially. So first, what happens when it's working? So we're going to look at this, and we just started this the last time. And so I intend to play through this a couple of times. You could think about, why does the green graph stay relatively constant? The green graph is looking at the concentration of solids in the green rectangle at the very top of this system. The red one is from the red rectangle, and look at the red one. Right there it crosses, and you can see that the red line went up really, really fast as the suspension crossed that red box. Does that make sense? We're looking in the red box and we're figuring out what the concentration is. Okay, so that was one. Let's do it again. You can see that there are things settling out on the incline. There is some interesting behavior on the incline that I don't actually understand. And maybe it's a little bit dark, but you can see that it looks like there'd be some interesting things happening at the very bottom of this. And you see that it grows quickly. Granted, the time is sped up a lot. We're at 14 hours right now, 15 hours, 16 hours. And you see the flock hopper kick into action right there. It's going to kick into action, and you can actually see the flock hopper filling up. Should we do that one more time? So notice that the blue line, which is the turbidity coming out of the tube settlers that are at the top of this, once the flock filter starts forming, those numbers start dropping. And so the blue line is dropping here. And that is because the flock filters are successfully capturing particles that otherwise would have gone right through the plate settlers. I'd just be happy to take any questions now about what you saw and what left you puzzled about what you saw. Anyone?
I have a question.
Yeah.
Is there any reason why the bottom of the hopper, not the hopper, the sedimentation tank, changed from having two slopes to just one and one vertical wall?
Yes, that was just because we wanted to make a smaller experimental apparatus. And we thought that if we modeled half of the width of a sedimentation tank, that would be enough to capture most of the physics.
Cool.
Good question. Other questions? Something that you saw that was a puzzle? Okay, I think I'm going to let you read that slide at your leisure, because you don't like it when I read text, I'm guessing. So we'll go to the next one. So let's think about this for a second. What happens if we have a system that's up and working, and then what happens if I slow the flow rate down? So real plants don't always operate at the design flow rate. Matter of fact, they often don't operate at the design flow rate. And so if they don't need as much water, they operate slower. And then the question is, well, what happens inside this system if the flow rate is slower? So could you think for a second about what do you think would change if the flow rate through this system slows down? Oh man, that's hard. I should have asked this question later after we saw more videos. Maybe I'll come back to this. Unless someone wants to jump in with an idea, what you think might happen when you slow this down. Oh, and it's also good to try Monroe's idea of just go to extremes. What if you slow it down a lot? Then what's going to happen? Maybe you will see it. You've got this suspension of particles that you're succeeding in resuspending. Can you imagine what happens to the concentration of that suspension of flocks if the flow rate or velocity up through them decreases, slows down a lot? What happens to that concentration of flocks?
Would it increase? Be a lot
It,
more congested?
that's exactly right. You're exactly right. You'd end up with a lot higher concentration of flocks in the Floc filter. And that means that they're dropping down onto the incline part of the bottom of the sedimentation tank, and then sliding back down to where the jet reverser is resuspending them again. And that means it's actually harder to keep that system in suspension because it's much more concentrated. And so if you slow down one of these tanks too much, it will fail. The Floc filter will actually collapse. So there's a failure mode, and it seems we have to think about what are we going to do about that. There is one nice option that we have inside an agua clara plant, and this would be not unique to us, but you should be able to turn off. You'll have multiple sedimentation tank systems in parallel, and you could always take one or more out of service so that the other ones keep on running at a reasonable rate. So that's one way to get around that problem. But I note here that we don't have the equations to describe this yet. So there's more work to be done. And here's another one. The operator would like to know what's going on both inside the Floc hopper and also being able to see what's happening inside the Floc filter. And you're looking at it from up above, and you could conceivably, and actually operators do this, if you shine a flashlight down between plate settlers, you can actually see down to the top of the Floc filter. So that's one way that you can kind of tell what's going on. But it's awkward because this system is kind of buried in concrete underneath the plate settlers, and so you can't see it very well. Okay, so now we're going to talk about what we discovered about this jet reverser system that's at the very bottom. So this jet reverser is the key to make this whole system work. And it was invented in the labs at Cornell with that apparatus that I showed you by playing with various designs and seeing what went wrong. So this is our current design. There's a little 3-inch pipe at the bottom, very bottom of the tank in the middle. And the diffusers, the pipes that are bringing the water in from the flocculator, are shooting down into that half pipe. And that's what's causing the flocks to be resuspended. So here's a few videos for fun. The video on the left is we're testing out the design that we were actually building in Honduras. And the design in Honduras had a flat bottom with a diffuser just blasting flocculated water onto that flat bottom. And you see that it's not succeeding in making a Floc filter. And there's a huge contrast with the one on the right, where it grows very quickly. And the one on the right has the jet reverser installed. So it's interesting looking at the one on the left, and look at what's happening right now. There's sediment accumulating in the bottom of the tank, and it's slowly working its way in. And it's almost like that sediment is like knocking on us and saying, look, if you made a little round thing down here, it would work. See that? Like the sediment is actually making the form that it needs to be in order for it to work. The problem with the sediment is that it's not stable. And so it keeps on eating away and then coming back. And so that system never works. And that explains why the plants that we built in Honduras that had flat bottoms didn't work. And so there was this great insight. You need a jet reverser in the bottom where you're very much controlling which direction the water takes that you're injecting into the bottom of the tank. Here's some more videos of this same kind of problem. So flat bottom, centered and offset. And I have a colleague, Len Lyon, that I worked with for many, many years, and good friend. And we would be advising students, and we would essentially take bets, although there was no money involved, but we would essentially take bets about which system would be better. And then the students would do the experiment, and then unfortunately, one of us would be proven wrong and one of us would be right. And I felt like the world is beautiful, physics is beautiful, there are beautiful equations, axisymmetric is beautiful. So the best design here will be an axisymmetric system with a centered jet. And Len Lyon said, nah, he thinks it's going to be axisymmetric. He thinks it's going to be non-symmetric, that it's going to be better with the inlet off to the side. And guess what? He was so right. Off to the side, it's completely stable. It forms a floc blanket very, very quickly, and there's never any failure that shows up right at the bottom of this tank. Whereas when you're injecting dead center, that jet that you're injecting dead center, the jet can, with relatively little force exerted on it, can decide to go more into one direction than in the other direction. And what happens is sediment can accumulate on the one side more, and that will push the jet away from that sediment. And because that jet can be easily deflected, it's not always stable. And you can see that, like in the video right now, you see that the jet is kind of going more towards the left and less towards the right, because the sediment is coming in further on the right side. So it's better to not give the jet a choice and to put it in on the one side of the jet reverser, so that its only choice is to go around like this. Anybody want to ask a question about that jet reverser design? I want to do this video, or this is an animation to help explain what's going on. So the inlet diffuser is bringing flocs from the flocculator, and they are going on up to the plate settlers. Eventually, some of them come back down as bigger flocs, and those bigger flocs, eventually, some of them land on the sloped part of the bottom of the sedimentation tank, because gravity is working everywhere. And so when they do, that slope is steep enough that they slide down. And then they slide into where the jet is coming up. So the jet reverser jet comes around the bottom here, comes up right here. And so it resuspends any particles, any flocs that are sliding down that incline. And then at this point, you should be asking, well, what about the other side of the tank? There's another incline. What do those flocs do? So we'll turn that on. So the floc on the other side does that. Goes down to the incline, slides around, and gets carried the whole way around the jet reverser. Now, any questions about what this jet reverser is doing?
I have a quick question. And so that inlet diffuser, that doesn't for like the flocs that come back down to the inlet diffuser and then shoot back up. The inlet diffuser, that doesn't like break up the flocs at all that have already formed.
Excellent question. That is definitely on the edge of knowledge. So great question, Eric. It's a great question. So we know that if that diffuser has a really high velocity or really high velocity gradient when that jet is spinning apart, that it does break up flocks and breaks them so small that they come out the top of the plate settlers. So it is possible for the inlet diffuser to break up what would have been green flocks and make them red ones. That's bad. What's interesting though is it also all the time breaking up blue ones and turning them into green ones? Or not? There's more we have to learn there. What we do know is if the velocity gradient is too high in the jet coming off of that inlet diffuser, it does cause performance to deteriorate. Other questions? But apparently it doesn't turn blue flocks with lots of red particles inside them into clean blue flocks. Somehow it's not doing that transition for us, which would have been amazing. That would have been great. Any question about like where this is happening? Where this is in the plant? This all makes sense? Thumbs up or thumbs sideways, I'm confused, or thumbs down, I have no idea what's going on. So for those of you who are kind of, I'd love to hear a question. Go ahead.
So the outlet, so all this comes from the flocculator, and so the outlet for the flocculator, where is that again in relation to the inlet for the sedimentation tank?
Okay, that's a great question. Let me see, can I? Where's the fast way to travel inside a presentation? I want just a big picture. Okay, so here's the sedimentation tank. The water from the flocculator was entering right here. So this wall of the sedimentation tank lines up with the wall of the flocculator. So the flocculator then flows into this first channel, which is this channel where I have the arrow drawn here. And then in that channel, there are pipes that go down to the very bottom of the sedimentation tank system.
So those two holes right there in the top picture, yeah, are those the inlet diffusers that lead to the sedimentation tank?
So those are connected to the inlet manifold, which we're looking at the end view of here. So this is the end view of that pipe that's buried. We can't see it in this view because there's concrete here. But here we see the end view of that manifold pipe, and then the diffusers are coming out of the bottom of that pipe. So the manifold might be 8 inches in diameter. Okay, and then the diffusers are 1-inch diameter pipes that are flattened to make slots. There's another view of that. Does that help more? See the inlet manifold, diffusers coming out the bottom, squirting water down into that jet reverser. Oh, and like everything is underwater. Like the water level in this tank is 10 centimeters down from the top. It's right up here somewhere. It's above the effluent manifold. Who else wants to ask a question about what's going on here? I know there was more questions there. You're just trying to figure out how to ask a question. Hannah, Michael, Kenzie, anyone there have a question? I know you were all like not quite clear about thumbs up or not.
I have one more, just a quick little extra thing too. So when it goes in the inlet influent manifold there, when the particles come down, are they exiting the influent manifold like all along the influent manifold, or just at the very end, there?
All along. So there are
Okay.
maybe 50 pipes coming out of that inlet manifold, and each one is carrying a little bit of water. And that's important because there are particles that are sliding down the slope of the bottom of the tank, and you have to resuspend them along the entire length of the tank. If there was any spot where we didn't have one of these diffusers aimed down into the jet reverser, Flocs would settle there.
Okay, great. Thank you.
Happy to take another question. I'm going to slide back to where we were in this presentation. Anyone else? Okay, so let's keep on going. And just to note that you can turn off one of these tanks, turn the water the whole way off, and then turn it back on again. And we at least have evidence of frequent success with doing that. So it means that even though the Flocs settle out and form some sludge in the bottom of the tank, when you turn it back on again, that jet coming out of the inlet diffuser is enough to resuspend things. So another view close up of that jet showing water squirting out of, ooh, hang on. Well, okay, that's good enough. And you might wonder, like, why are we caring so much about this geometry? We ran into multiple problems with having sludge in the bottom of sedimentation tanks, and I'll show you some more of that later on. But one of the issues is that sludge goes anaerobic, and anaerobic means it produces methane, and that means that you've got little methane bubbles coming up through the water column in the tank. And I don't know if you can think about, like, if you turn this Floc filter tank system into a soda bottle with little bubbles coming up through it, what those bubbles do is they grab a hold of Flocs and carry Flocs straight up to the top. So bubbles in one of these tanks is very, very bad. Actually, there's another treatment process called dissolved air flotation that uses that technique, but you have to decide which one are you going to use. Either you use dissolved air flotation and you collect the dirt off the top of your tank, or you use sedimentation and you collect the dirt off the bottom of your tank, and you don't want to try doing both of those at the same time. So our insight is that these tanks should have no settled sludge. There should be no sludge. It's just hanging out in the tank settled, because if it's settled, it'll go anaerobic. Whereas if it's in suspension, it won't go anaerobic, even if there is biological activity there, because there's enough oxygen in the water to keep it aerobic. And then I talked earlier about what happens if you slow it down. And this is an example of that. If we're using two different diameters of the tube that's injecting water into the bottom of this tiny little sedimentation tank, and we're keeping the flow rate the same. So that means that when we decrease the diameter of the tube, the velocity is higher. So if you look at on the left, there's a 3.9 millimeter diameter tube as the inlet. That has a high velocity. And on the right is an 8.9 millimeter, and it has a lower velocity. And as the jet gets bigger in diameter and is traveling slower, it becomes more vulnerable to the sludge actually coming in further and overtaking it and like burying the jet reverser. And so that's the idea that theta2 is greater than theta1. The sludge is actually coming in further onto that jet because that jet doesn't have as much momentum. I think I'm going to pass on this because it's too hard. I would love to have you do a breakout, but we're not going to bother doing that just a little bit of time that we have. So I'm going to go on to the floc hopper. So the floc hopper is where all the flocs come to that are excess flocs that are coming out of the floc filter, and they're accumulating in the floc hopper. And so the question is, well, how do we design the required size of the floc hopper? Because in our design thinking says that every dimension matters. And there's got to be something that determines how big this floc hopper has to be. And there's this notion that if you make it too small, it's going to fail somehow in this case. And if you make it too big, it's expensive. So we want to make it smaller. And the question is, what fails when you make it too small? The truth is, we don't have great equations for this yet, but we have at least some insight. But we have more to do as far as incorporating this into our design. This is a cool video to show at the very top of the floc hopper, sorry, very top of the floc filter, shows the flowing of the flocs over the top of the weir. That was too weird, wasn't it? Should we look at that again? I love the puzzled faces that I'm seeing. Do you believe this? Like, this is real. This video is in real time. It's not been sped up or slowed down. And it's showing what's right up here when this floc filter had grown up to be as tall as the weir. And you see this lovely thing of these flocs falling down, and it's like it's in slow motion. And it's like Niagara Falls. Like this is a fluid coming over the edge of a falls and it's falling down. But the reason that it falls so slowly is because the difference in density between the flocs plus water compared with water, that difference in density is very tiny. And it's the difference in density that determines how fast the flocs plus water are going to fall inside the water. If you want to convert that back to Niagara Falls, it's the difference in density between water and air that determines how fast the water over Niagara Falls falls down. If Niagara Falls was full of water below the falls, then there would be no falling over because the density of the incoming fluid and the density of the fluid that's there is zero. The difference is zero, and so there would be no velocity. Here, it's just a tiny difference in velocity. Flocs plus water are just a tiny bit more dense than water, and so it falls over like in slow motion. And that is happening right here inside the tank. This weir is what's setting the height that the floc filter grows to. So this is my idea of how we would need to design the floc hopper. First of all, we know that the weir controls how deep the floc filter is. The floc filter flow rate, the rate of flow out of the floc filter into the hopper. So it's the rate of that red stuff falling over the top of that hopper is a function of, this is based on mass conservation. It's based on the mass flux of particles into the sedimentation tank from the flocculator. So almost all of the particles that come from the flocculator end up finally exiting the sedimentation tank or by falling over that weir. And because mass must be conserved, that's the concentration of clay or particles that have to be falling over that weir. So that's this notion that what's going in, the flow rate through your sedimentation tank times the concentration of flocks that are coming out of the flocculator must equal the flow rate into the hopper times the concentration of the floc filter, which is what's falling into the hopper. So that's just a statement of mass conservation. You can solve that for what the flow rate is over that weir. And that flow rate over the weir is usually small, although not always small. And then there's this other insight, and that is the velocity up through the floc filter in our systems is 1 millimeter per second, okay? And if we just suddenly turned the flow off to one of our sedimentation tanks, then the flow upward is 0 millimeters per second. And now the question is, how fast is the floc filter going to settle down? You see the question? Normally, the floc filter is not settling down at all. The upflow velocity is 1 millimeter per second. If I turn that off, how fast does the floc filter drop? And the insight is, you just change your frame of reference. It's relative velocity in both cases. The relative velocity between the flocks and the water is always the same. So if you stop the water, the flocks are now going to drop at 1 millimeter per second. So if you suddenly turn off the flow, the floc filter is going to settle at 1 millimeter per second. And that means that the flocks that you send from the floc filter into the floc hopper are also settling at 1 millimeter per second. That's how fast they consolidate. And so that is the VZFF. That's the average velocity upward in the floc filter is 1 millimeter per second. And that velocity times the area of the floc hopper must equal the flow rate of flocks into the floc hopper. And so that gives us a way to calculate the area that we need for that floc hopper, the plan view area for the floc hopper. There it is. We haven't yet used this for the design of our tanks because there's been another constraint that set this dimension, but this is at least what the theory would lead us to. The problem is that we don't have good numbers yet on what the concentration of particles is in the floc filter. So with that, I want to end today and first take any questions. Anybody want to ask a question about floc hoppers, floc filters, a crazy video that I showed you that made no sense? Anyone? Okay. When I come around to you in your groups in Gather, I would love to hear any questions. So if you maybe would spend the first couple minutes in Gather talking about what you just learned and what was puzzling. And that way, when I come around, you can bring up your questions. I realize it's always easier if you can ask your questions to your peers first and realize that actually your question was not a stupid question. It was a very good question. So go ahead, figure out your questions in groups, and then start working on the flocculator again. Any announcements before we split? Okay, jump in together. I'll see you there.